Welcome to our channel. Today, we're diving into the fascinating world of quantum computing. Imagine solving problems that today's supercomputers can't handle. That's the promise of quantum computing. Get ready to explore how this revolutionary technology works and what it means for the future. Let's get started. Hi everyone, and today we're uncovering the mysteries of quantum computing. What exactly is quantum computing and why is it such a game changer? If you're curious about the future of technology, stick around, because we're about to explore some mind-blowing concepts. So, what is quantum computing? Simply put, it's a new way of processing information using the principles of quantum mechanics. Unlike classical computers that use bits, quantum computers use qubits, which can exist in multiple states at once, thanks to a property called superposition. Imagine being able to solve complex problems in seconds that would take classical computers years to compute. That's the power of quantum computing. IBM Quantum, for example, is making real quantum hardware available to developers worldwide, pushing the boundaries of what's possible. Our superconducting quantum processors are becoming more powerful with each iteration, driving towards the speed and capacity needed to change the world. These quantum machines are fundamentally different from the classical computers we've been using for decades. They open up new possibilities for solving some of the world's toughest problems. Why do we need quantum computers? Let's take an example: simulating molecular behavior. Classical computers struggle with this because of the sheer complexity. Quantum computers, on the other hand, can handle these complex simulations efficiently, potentially revolutionizing fields like medicine and semiconductor design. Quantum algorithms create multidimensional computational spaces, offering a new approach to complex problem solving. This is where quantum computers truly shine, providing solutions where classical computers fail. Quantum processors operate at incredibly low temperatures, just above absolute zero, to maintain their quantum states. This involves using superconductors and specialized cooling systems, creating an environment where electrons can move without resistance. Superposition and entanglement are key phenomena in quantum computing. They enable qubits to perform multiple calculations simultaneously, exponentially increasing computational power. Right now, IBM Quantum is leading the charge in quantum computing. Their Qiskit Quantum SDK and Qiskit Runtime are paving the way for developers to build and scale quantum applications. Imagine solving real-world problems faster and more efficiently than ever before. Qiskit Runtime enables seamless integration of quantum and classical computing, significantly speeding up computations. It's an exciting time for researchers and developers in the quantum field. But let's take a step back. Why exactly do we need quantum computers in the first place? When scientists and engineers encounter incredibly difficult problems, they turn to supercomputers. These are massive classical computers with thousands of CPU and GPU cores, capable of running large-scale calculations and advanced AI. However, even these powerful machines struggle with certain types of problems. Supercomputers often get stumped by problems that involve a high degree of complexity. Complexity, in this context, means a lot of variables interacting in complicated ways. For example, modeling the behavior of individual atoms in a molecule, or identifying subtle patterns of fraud in financial transactions. These are problems that classical computers can't solve at any scale. The real world operates on quantum physics. Computers that use quantum bits, or qubits, to make calculations should, in many cases, be our best tools for understanding it. Let's look at an example. A classical computer might excel at sorting through a vast database of molecules, but it struggles with simulating how those molecules behave. Today, if scientists want to know how a molecule will behave, they must synthesize it and experiment with it in the real world. If they want to see how a slight tweak would impact its behavior, they usually need to synthesize the new version and run their experiment all over again. This is an expensive, time-consuming process that hinders progress in fields as diverse as medicine and semiconductor design. A classical supercomputer might try to simulate molecular behavior with brute force, using its many processors to explore every possible way every part of the molecule might behave. But as it moves past the simplest molecules, the supercomputer stalls. No computer has the working memory to handle all the possible permutations of molecular behavior using any known methods. Quantum algorithms take a new approach to these sorts of complex problems, creating multi-dimensional computational spaces. This turns out to be a much more efficient way of solving complex problems like chemical simulations. We don't have a good way to create these computational spaces with classical computers, which limits their usefulness without quantum computation. Industrial chemists are already exploring ways to integrate quantum methods into their work. This is just one example. Engineering firms, financial institutions, and global shipping companies are exploring use cases where quantum computers could solve important problems in their fields. An explosion of benefits from quantum research and development is on the horizon. As quantum hardware scales and quantum algorithms advance, many big, important problems like molecular simulation should find solutions. An IBM quantum processor is a wafer not much bigger than the one found in a laptop. A quantum hardware system is about the size of a car, made up mostly of cooling systems to keep the superconducting processor at its ultra-cold operational temperature. A classical processor uses classical bits to perform its operations. A quantum computer uses qubits, CU-bits, to run multi-dimensional quantum algorithms. These qubits need to be very cold, about 1/100th of a degree above absolute zero, to avoid decoherence, or losing their quantum states. To achieve this, we use supercooled superfluids. At these ultra-low temperatures, certain materials exhibit an important quantum mechanical effect. Electrons move through them without resistance, making them superconductors. When electrons pass through superconductors, they match up, forming Cooper pairs. These pairs can carry a charge across barriers, or insulators, through a process known as quantum tunneling. Two superconductors placed on either side of an insulator form a Josephson junction. Our quantum computers use Josephson junctions as superconducting qubits. By firing microwave photons at these qubits, we can control their behavior and get them to hold, change, and read out individual units of quantum information. A qubit itself isn't very useful, but it can perform an important trick. Placing the quantum information, it holds into a state of superposition, which represents a combination of all possible configurations of the qubit. Groups of qubits in superposition can create complex, multi-dimensional computational spaces. Complex problems can be represented in new ways in these spaces. Quantum entanglement is another key phenomenon. It correlates the behavior of two separate qubits. When two qubits are entangled, changes to one qubit directly impact the other, no matter the distance between them. In an environment of entangled qubits placed into a state of superposition, there are waves of probabilities. These are the probabilities of the outcomes of a measurement of the system. These waves can build on each other when many of them peak at a particular outcome, or cancel each other out when peaks and troughs interact. These are both forms of interference. A computation on a quantum computer works by preparing a superposition of all possible computational states. A quantum circuit, prepared by the user, uses interference selectively on the components of the superposition according to an algorithm. Many possible outcomes are canceled out through interference, while others are amplified. The amplified outcomes are the solutions to the computation. Right now, IBM Quantum leads the world in quantum computing hardware and software. Their roadmap is a clear, detailed plan to scale quantum processors, overcome the scaling problem, and build the hardware necessary for quantum advantage in the era of noisy quantum machines. Today, a significant amount of work in the field of quantum computing is devoted to realizing error correction, a technique that would enable noise-free quantum computation on very large quantum computers. Recent work from IBM and elsewhere has shown that noisy quantum computers might be able to do useful work in the near future, even before the advent of error correction, by using techniques known as error mitigation. IBM has spent years advancing the software necessary to do that useful work. They introduced the Qiskit Quantum SDK. It is open source, Python-based, and by far the most widely used quantum SDK in the world. Useful for executions both on IBM's fleet of superconducting quantum computers and on systems that use alternative technologies like ions trapped in magnetic fields. Qiskit Runtime, the most powerful quantum programming model in the world, enables users to deploy custom quantum classical applications with easy access to HPC hybrid computations on the highest performing quantum systems in the world. Qiskit Runtime provides an execution environment for weaving together quantum circuits with classical processing, natively accelerating the execution of certain quantum programs. This means faster iteration, reduced latency, and more uninhibited compute time on the world's leading quantum systems. Qiskit Runtime's cloud-based execution model demonstrated a 120x speedup in simulating molecular behavior. The future of quantum computing holds endless possibilities. From advancing medical research to optimizing global logistics, the impact of quantum computing will be profound. What questions do you have about quantum computing? Share them in the comments below. Thanks for joining us on this journey into the future of quantum computing. Don't forget to like, subscribe, and hit the bell icon for more exciting content. Until next time, stay curious and keep exploring.